Good day everybody. Welcome to my course on upheaval buckling calculation for onshore pipelines using OTC 6335 method. So in this course we will be specifically explaining the methodology of upheaval buckling calculation, the steps, background formulas for onshore pipeline systems. Means this application or this method is not covering the offshore pipelines. Specifically, I will be explaining the details related to onshore pipelines and the method that is or that will be used for this course, specifically for the practical case study purpose as well as the background formula and theory purpose. It will be OTC 6335 method. In this image, you can see that two pipelines are showing which has moved vertically upward direction from the soil. In general or in actual installation stage, the pipeline was installed buried. So due to some reason, the pipeline has moved in upward direction or displaced in upward direction to cause a bend, as you can see here. So this type of situations, if arises in any buried pipeline systems, is known as upheaval buckling. The methodology or phenomena is buckling, means the pipeline has buckled and it is in vertical direction. That is the reason it is called upheaval buckling. There is one more type of buckling that is known as lateral buckling. In general, for onshore pipeline systems, lateral buckling is not a governing case because you can understand easily that when you are installing any pipeline inside a trench, the lateral side soil resistance will be very high, such that it will not allow the pipeline to move in lateral direction. However, towards the upward direction or vertical direction, only resistance will be the depth of cover of the soil. So, and based on the actual depth of cover and the forces that are generated because of temperature, pressure and other reasons, the pipeline can easily displace that soil cover and come outward, as you can see in these two images. So you will try to learn the methodologies for performing upheaval buckling calculation using OTC 6335 method. Let's move on or dive in to the course. Now in this course, we will cover the following. First, a brief introduction, and then I will explain that what is pipeline upheaval buckling, what are the main reasons for upheaval buckling, then what are the key parameters that impact the upheaval buckling, then what are the available methods for upheaval buckling, and out of this method in this course we will be learning the steps for upheaval buckling calculation using OTC 6335 method, and at the end we will be checking one practical calculation example and we will try to understand that what are the output result that we are getting because of this calculation and how to implement this in our design. Hope the course content is clear. Let's move on to the next slide. Now, who is this course for? Means who are the actual candidates or who will be benefited by attending this course? Now, a course on upheaval buckling calculation for onshore pipelines is ideal for professionals involved in pipeline design, installation and integrity management, especially those working in engineering, construction or operations where buried or trenched pipelines are subjected to thermal expansion or soil restraint effects. In general, this course will be suitable for pipeline design engineers who are designing the pipeline systems. So during their design phase, they can perform this calculation to avoid the possibility of upheaval buckling. Then stress and structural engineers, in most of the organization, the calculation is performed by pipeline stress engineers. So they also will be benefited by taking this course. Then pipeline construction and installation engineers, pipeline integrity and maintenance engineers, engineering consultants and EPC contractors, graduate students and early career professionals, pipeline operators and asset owners. So all this group of people or group of professionals will be benefited or will get a basic idea of upheaval buckling calculation methodology, and if they are reviewing any document or they want to uplift their knowledge on upheaval buckling, they will be benefited from this online course. Now let's learn what is upheaval buckling in onshore pipelines. Now in simple terms, when a buried pipeline gets heated up during operation, it tends to expand in length. That is a well-known fact that if a pipeline is buried, we can assume that both ends of that pipeline are fixed. So let's assume that those are acting as an anchor. Now when temperature changes from installed to design temperature or operating temperature, due to that temperature difference, there will be a generation of thermal force, which in turn will result a thermal stress in the pipeline system. Now because of that force, it will try to buckle. Now if the soil that is present there on top of that pipeline is not sufficient and in weak nature, then it can force the pipeline to move in upward direction, causing upheaval buckling. So one of the cause you can assume as the temperature difference from the installed to the design temperature. Again, if the soil around it does not allow it to move freely, then the pipeline experiences an axial compressive stress. When this stress becomes large enough to overcome the downward resistance provided by the soil cover, the pipeline can buckle upward, forming a wave-like deformation. This phenomenon is called upheaval buckling. So upheaval buckling can be defined as the upward movement or deformation of a buried pipeline due to compressive axial forces, most commonly caused by thermal expansion. This is one of the main factor. Second main factor is internal pressure, and sometimes due to soil movement when the pipeline is restrained by the surrounding soil. But in this specific course, we will be explaining the first two causes, that is thermal expansion and internal pressure. Now the basic mechanism of upheaval buckling is a buried pipeline is subjected to axial compressive force due to thermal expansion from hot transported fluid, then internal pressure that causes a Poisson effect because of shortening, and end restraints or bends that prevent free expansion. What I was explaining, that towards the end you can consider that it is similar to anchor, not exact anchor, because soil has some stiffness, and based on that stiffness it will be slightly, we can consider or we can assume basically not fixed anchor, but it will be giving a philosophy similar to anchor. Now the soil cover above the pipeline provides vertical restraint that is known as uplift resistance. Now when the compressive force exceeds a critical value, the pipeline snaps upward locally, creating a buckle shape. similar to how a compressed column bends when overloaded. So that is basically the meaning of upheaval buckling. So if a straight pipeline is there, it may snap upward direction, removing or avoiding the resistance provided by the soil cover or overcoming the resistance that soil cover provides. Then in that situation, the pipeline is said to be buckled in a vertical direction, or upheaval buckling happened. Now this is the sequence of events that usually happens in upheaval buckling. That during as-laid condition, the pipeline will be in this condition. As we all know that the pipeline will not be continuously straight, because due to soil terrain there will be some discontinuities in between. So pipeline will be laid in, not in a straight, otherwise you can say in a curvical manner. Then on top of that we will be giving the soil, and the actual trenched and buried pipeline will be as shown in B. So this is the pipeline over which we will be adding the soil cover. Then when fluid will be flowing through these, so during installation there will be, the pipeline will be at a temperature, and when fluid will be flowing it will be at a different temperature, and because of that the pipeline will tend to deform due to that thermal change. And also, as I mentioned, that internal design pressure is also causing this displacement or movement. Now when this force, compressive force, that is generated because of internal design pressure as well as temperature of the fluid, becomes such that the pipeline pushes in upward direction against cover, and it takes the shape of as shown in D. So during that time we can say that the pipeline has buckled, or upheaval buckling happened. So these are the 4 steps by which upheaval buckling happens in an onshore pipeline system. Now key factors that influence upheaval buckling. The main causes of upheaval buckling are: first is thermal expansion from temperature increase during operation, then internal pressure expansion, inadequate burial depth or soil cover, low soil stiffness or weak backfill, imperfections in pipeline alignments, example initial vertical imperfection or bends, as I was showing in last slide, that in between the actual pipeline and the soil profile there are certain gaps, there could be certain gaps. So those gaps will be helping the pipeline to cause upheaval buckling. Those are known as imperfections. So in those imperfection regions the tendency or possibility of upheaval buckling increases. That we will basically see, not in this course, but I am planning to make another course uh, using Peters method. So in that method, that imperfection heights are important. In this course also there will be consideration of imperfection height that we will be seeing or explaining during the equations. That imperfection height plays an important role, because what happens, basically due to that imperfection height the actual soil cover or effect of actual soil depth of cover reduces. So let's assume that your pipeline has a soil depth of cover of 1 meter, means 1000 mm, and at the bottom of pipe there is a imperfection height of 200 mm. So in those regions the soil cover, even though it is 1 meter, its effect will be around 1000 mm minus 200 mm. See, so roughly 800 mm soil cover actually will be protecting or giving resistance to the compressive displacement that is happening because of the axial compressive force. So this way, when we will be learning the actual steps or formulas, we will be seeing the impact of imperfections that that is there during soil terrain and the actual nature of onshore pipeline systems. So basically we understood that the key influencing upheaval buckling parameters are pipeline parameters, means diameter, wall thickness, material stiffness, burial depth. Then thermal and pressure effects, high operating temperature and pressure leading to greater axial compression. Then soil properties, means soil density, cohesion, friction angle, compactness of backfill material, etc. Then installation conditions, trench geometry, bending imperfections or insufficient backfill compaction, etc. External loads, ground movement, seismic activity, differential settlement, etc. These are some of the other causes of upheaval buckling, but in this course we will not be explaining these terms. We will simply concentrate the upheaval buckling because of temperature change and internal design pressure. Now, why should I worry about upheaval buckling? Means even though there is a upheaval buckling in a system, what is the concern that we are so worried about this? We are worried because the upheaval buckling can lead to pipeline failure and loss of integrity. When a buried pipeline experiences axial compressive forces from temperature rise or internal pressure and the soil cover is not sufficient, the pipe can buckle upward. This upward movement can cause excessive bending stress in the pipe wall, local plastic deformation, coating damage or disbondment, fatigue or eventual rupture. Even a small uplift can compromise the mechanical integrity of the pipeline. Next, it can expose the pipeline to external damages. A pipeline that buckles and rises towards the surface may become exposed or come closer to the ground surface. This exposure can lead to mechanical damage from vehicles, machinery or erosion, loss of protective soil cover, reducing thermal and mechanical stability, increased risk of corrosion if coating and cathodic protection systems are damaged. Then it can cause operational issues. Upheaval buckling introduces unexpected displacement and stresses which can affect flow efficiency due to local bending and internal turbulence, cause misalignment at welded joints, create cyclic stresses under temperature variations, reducing pipeline life. So the main factors because of which we should perform upheaval buckling are loss of pipeline stability, damage to coating or insulation system, reduced structural integrity or potential rupture, flow restriction and operational hazard due to pipe deformation, increased maintenance costs and potential environmental risks. Now, when to perform upheaval buckling analysis? Now, upheaval buckling analysis should be performed whenever a buried pipeline is expected to experience significant compressive axial loads, typically caused by thermal expansion and or internal design pressure. Let's break down this by stages. So during design phase, always for hot and pressurized pipelines, perform upheaval buckling analysis during pipeline design if the pipeline will operate at elevated temperature. For example, crude oil, multiphase and hot water lines, etc. There are significant pressure variations between operating and shutdown conditions. So during that time also you should perform. Then the pipeline is buried and soil provides restraint that can trap axial forces. The line runs over undulating terrain or has vertical imperfections in its profile. The burial depth is shallow or soil type is weak, reducing uplift resistance. So these are some of the reasons for which or stages for which you can perform your upheaval buckling during design stage. Next is when temperature or pressure changes significantly during operation. Again, when terrain profile or soil conditions are unfavorable or favorable to upheaval buckling. Next is during construction or installation modifications. To reassess the upheaval buckling potential, you have to perform this. Finally, during integrity management and fitness for service reviews. So in all those stages, you can perform upheaval buckling analysis. So upheaval buckling analysis should be performed whenever a buried pipeline is expected to experience significant compressive axial loads, typically caused by thermal expansion, internal pressure, or soil restraint. Now, difference between upheaval buckling and lateral buckling. During initial discussion, I have mentioned that there is one more term known as lateral buckling. So there are basically two types of buckling. One is known as upheaval buckling and other is lateral buckling. As you already understood by now that upheaval buckling means vertical movement, pipeline lifts upward direction as you can see in this image. And lateral buckling means horizontal movement, means pipeline snakes sideways, so it moves towards in sideways direction. You see that this white line is the actual installed position of the pipeline, whereas due to lateral buckling the pipeline has moved laterally, and this is known as lateral buckling. Both are driven by axial compressive forces, but soil restraint direction and imperfection orientation determine which mode dominates. In case of onshore pipeline systems, basically upheaval buckling dominates, whereas for offshore, when it is in surface laid condition or near the sea bottom, there it lateral buckling also may dominate. So for offshore pipeline systems or uniformly distributed pipeline systems, means surface laid pipelines, in those situations lateral buckling calculation also you need to perform, which is not scope of this course. So hope you understood that what are the basic meaning of upheaval buckling, what are the main factors that causes upheaval buckling, what are the method that we are going to explain in this calculation or in this course for upheaval buckling calculation. And that's all for this specific introduction module. Thank you. Happy learning.